So I know your question was just specifically about 8b and writing the equation in the form that models this situation in the form A equals PE to the RT power. But I think it will be helpful for us to do that if we just talk through the entire problem. So first off, we know that the half-life of caffeine is 5 hours. This means the amount of caffeine in your bloodstream is reduced by 50% every 5 hours. A grande French roast is 330 milligrams of caffeine. So let Q of T denote the amount of caffeine in your system T hours after consuming your grande French roast. For simplicity, assume that the entire grande French roast is consumed instantly, so that you instantly have 330 milligrams of caffeine in your system. So let's go back to the general model of exponential growth and decay to come up with our first equation that models this situation. So we would have Q of T, the initial population will be that, or amount would be that 330 milligrams. And then we're given information about the decay rate, right? We're given that the half-life of the caffeine is 5 hours. So R in this case would be negative 0.5 or negative 1/2. And then we want our inputs to be time in hours, right? That was given to us in the wording of the problem. So since the half-life is 5 hours, 5 hours would be considered one period. So we're going to take the number of hours that have passed and divide by 5 in order to determine how many periods have occurred. Remember, the exponent represents the number of periods that have occurred. So where T is the number of hours that have passed. And this can be simplified to be 330 with the base written as 0.5 or 1/2 to the T over 5 power. So A asks us how many milligrams of caffeine will be in your system after 5 hours, after 10 hours, after 15 hours. So to find after 5 hours, well, that's just one period, right? So if we plug in 5, though, you can figure that out in your head, But if we want to use the equation of our function, right, that ends up being just 1/2 of 330, which is 165 milligrams. And for 10 hours, that's after 2 periods have occurred. But again, using our model here, that's 330 times 0.5 raised to the second power gives us 82.5 milligrams. And after 15 hours, that's after 3 periods have occurred, and I'm just plugging this into my calculator, although again, you could figure it out just from halving the previous amount. Oh, I wrote divided by 3 when I was saying 3 periods have occurred. But that ends up being 0.5 to the third power, right? Since 15 divided by 5 is 3. So that would be 41.25 milligrams. Okay, so now to answer question B, we're trying to come up with the equation in this form, so with base E, that would have the same inputs and outputs, so their graphs would actually match. When we have base E, we're thinking about a population of concern continuously changing. So in this case, you consume the grande French roast, you have the 330 milligrams in your system, and you don't have 330 milligrams in your system up to like that first period, right, of 5 hours, right? You don't go from having 330 milligrams all the way up to 5 hours having passed and then it immediately cut in half. You're losing a small amount, or the amount in your system is decreasing constantly. So in order to come up with this model, it's going to be the same initial amount of 330. So we could actually replace P, also known as A sub 0, as 330. And we need to figure out what R would be. So basically what the hourly rate would be, reflecting the fact that you are continuously, or the amount in your system is continuously decreasing. So in order to do that, we're actually going to use one of the other data points that we found. So like one of our answers from question A. We know that after 5 hours, there is 165 milligrams in our system. So I can substitute 165 in. 330 is still the initial amount, E, and then in for T, I'm going to substitute 5, right? Because after 5 hours, there's 165 milligrams left in your system. Okay, so if we divide by 330 on each side, we would have 1/2 equals E to the 5R power. And then rewriting in logarithmic form, that would be 5R equals to ln of 1/2. So R equals to ln of 1/2, 1/2, not 1/5, divided by 5. And we don't care what the approximation is for R. We're trying to find the equation with the base of E. So we want to use the exact value for R. So that would be ln of 1/2 over 5 times T, where T is still number of hours that have passed. And we can confirm that we found the correct value for R, or the correct equation, graphically by graphing both this equation and this equation. So y, I'm going to use x's and y's instead of t and q of t. So the first equation would be y equals to 330 times 0.5 to the x divided by 5 power. Okay, so there's that curve. And then we can now type in our equation that has base e, so still 330 times e to the, let me use parentheses to write this. I hit the function button. I'm using Desmos to type in ln of 1/2 divided by 5 times x. Okay, and you can see it's already overlapped. So if I take the second equation's graph off and then I put it on there, you can see they overlap perfectly because all of their inputs, they have the exact same points, all of their inputs and outputs. And you could actually prove, if you were to set these two equations equal to each other, you could prove that they represent the same thing. Okay, and then question C, you can use either equation to solve for how long it would take for there to be 5 milligrams of caffeine. So like if you wanted, I would probably use the first equation just because that doesn't already have an ln in it. Here, I'll switch colors again. So for question C, I would set the first equation equal to 5. And 5 divided by 330 simplifies to be 1/66. Okay, and then rewriting in logarithmic form would be t/5 equals to the log base 0.5 or 1/2 of 1/66. And then multiplying by 5 on each side, you would get t equals to 5 times the log base 0.5 of 1/66. And the units would be in hours. So this would represent the exact number of hours. It could be helpful to get an approximation, type that into our calculator in order to get the approximation, just so that we can kind of wrap our brains around how long it would take for there to be 5 milligrams left in our system. I get 33.222 hours for there to be 5 milligrams of caffeine left in your system after drinking a grande French roast coffee.